We know that reactions can be slow or fast. Ripening of a fruit, an explosion, burning, all of those are reactions. And sometimes we want some of those reactions to be faster than they normally are, and some of them to be slower than they normally are. For example, an explosion releases a lot of energy in a very small amount of time. But only if we could slow that down and get that same energy, but in longer amount of time, we could actually use that energy for something useful and constructive. As scientists have studied rate of reaction, the rate is basically how fast or slow the output is made during a reaction, the product is made during a reaction. So as scientists have studied that, they have figured out 5 different ways in which rate of reaction changes, or 5 different factors that affect the speed or rate of a reaction. But the underlying reasoning comes from another part which is called collusion theory. Collusion theory basically says that for a reaction to occur, let's suppose A wants to react with B to get C. Now, A particles must collide with the particles of B with correct orientation, which means they must collide with the right angles, and correct or sufficient energy. If they have sufficient energy and they have the right orientation, then A particles, when they collide with B particles, they will produce C. But if they're not doing that at the right angles, or they have less energy than required, then that will not lead us to getting C. In fact, that collision will be useless. So collisions that actually lead to production of this product, we call them successful collisions. And successful collisions are basically the ones that have the correct energy and they have the correct orientation. The minimum energy that is required for a reaction to start, that we know from energy changes chapter, is called activation energy. It is the minimum energy for a reaction to occur, which means that A must collide with B at least with the energy equal to activation energy of that reaction. And after this collision will be successful and lead us to C. All collisions that don't do this, they are not successful. Now that's the basic idea of collusion theory, which means that if you want to speed up a reaction, you just need to make sure that you increase the number or ratio of successful collisions that are happening in the same amount of time. So there's 2 factors here. One is time, which we want to reduce if you want to speed things up. And number 2 is collisions, frequency of collisions, number of successful collisions, which we want to increase. If we do this, we will be able to get a greater rate of reaction. Now there are 5 factors that do this, and all of them basically lead to greater number of successful collisions. So we say there's a greater frequency of successful collisions per unit time. And if we're able to do that, then we're able to basically, this will lead us to a greater rate of reaction. Now, what are those 5 factors? The first factor basically works on just solids, and that factor is surface area. The idea of surface area is basically that if you have a cube, then that cube, when particles want to collide with this thing, which is part of a cube, this cube, then they must collide over here. Now let's suppose there was a particle deep hidden inside the cube. Then any particle coming towards the side of this cube will not be able to approach this particle that's deep inside. But let's suppose I open this cube up, or I break it down into multiple slices. Now I have multiple different slices, and now all of these are open to collisions from external particles. So the idea is that if you have more particles that are exposed to these collisions, you will be able to get a greater rate of reaction. Why? Because the more the surface area, the greater the number of particles that are exposed for collisions, and so the greater the frequency of successful collisions per unit time, leading us to a greater rate of reaction. Now, because only particles that you can actually expose more are the ones that are part of a solid. So if you have a solid and you make powder out of it, you will expose more particles out for successful collision. So we can say the surface area depends on solids only, and it affects solids only. So if there's a reaction which you have a solid, you could speed it up by taking that solid in smaller particles like powder form. But if you have it in larger granules or lumps, then less particles are exposed at the same time, so less frequency of collisions per unit time, leading to a lower rate of reaction. Now the second factor that affects the rate of reaction is concentration. And that's a universal factor, which means that it affects the rate of reaction regardless of what state the particles are in. Concentration is how many particles you have in the given space that you have, like how many particles are in the same area or same region. And if you have greater number of particles, that means there's going to be a greater collision, greater chance of collision for them to have. So that means there's a greater frequency of successful collisions per unit time, leading us to a greater rate of reaction. So for example, if you use acids in a reaction and you have one acid that is concentrated and one acid that is dilute, the concentrated one will obviously have more particles in the same space, in the same volume of solution, which means that they will collide more and they will also give us greater frequency of successful collision per unit time. A point about concentration that you must know is that with greater concentration comes greater number of particles, which means that you're also going to get greater amount of output. If you take a certain amount and you break it down into smaller powder, you are not going to get a greater output. The output will still be the same, it will be just faster. With concentration, if you increase the concentration, you're also increasing the output that you get. So if one solution that is half a mole per dm cube is producing 20 cm cube of gas, a solution that is 1 mole per dm cube, which is double in the concentration, will also provide us with 40 cm cube of the gas. The volume of output will also be increased by the same ratio. So that's the idea of concentration. The third factor that affects this is temperature. Temperature is basically a measure of average kinetic energy. So kinetic energy makes things move. When they move, there's a chance of collision. And when there's more collisions, there's a greater frequency, greater chance of successful collisions happening in the same amount of time. And that's what temperature does. You increase the temperature, then you basically give them more kinetic energy. The average kinetic energy of the particles increases. Not all particles have the same energy, but the average increases, which means there is a greater chance that particles that need activation energy, they are now more. So basically, any collision that is happening with activation energy or more will be successful. With an increase in temperature, more particles have greater energy. So there's a greater chance that they will collide with activation energy. So you're going to get greater frequency of successful collisions per unit time, and that leads us to a greater rate of reaction. The next factor that we have is quite different from all of these, and that factor is pressure. What pressure does is basically that it affects gases only, just like surface area only affects solids. So with greater pressure, we have studied gas laws in the first chapter. With greater pressure, particles of the gas come closer together. The volume decreases, provided you keep the temperature the same, which means now particles are closer together. So if they're close together, there's a chance that they will collide more. And when they collide more, there's a chance that there'll be more of those collisions will be successful. And so there's a greater frequency of successful collisions. And lastly, the factor that affects rate of reaction is catalyst. Catalyst is interesting because it doesn't do anything to the particles. All of these factors were affecting particles in one way or another. Concentration was giving us more particles in the same amount, pressure was bringing the particles together of the gas, temperature was giving the particles more energy, and surface area was exposing the particles more. But catalyst is something that does change the nature of the reaction. It doesn't do anything to the particles. So catalyst, what it does is that it basically reduces the activation energy. So what was successful collision? It was a collision that was happening with the same correct angles and with the correct energy. Now that energy was obviously some value of activation energy. Catalyst has lowered that value. So now even particles who did not qualify for that collision, successful collision earlier on, Now they must also have, or there's a chance that they will have more energy than the new activation energy. Why? Because the new activation energy is much lower than the previous one. So more particles qualify for a successful collision. So catalyst basically lowers the activation energy. So all of these 5 factors then affect or increase the frequency of successful collision per unit time. Remember, the rate is always increased by frequency of collisions in the same amount of time or per unit time, which is why you must always discuss the factor of time as well. And so they increase the rate of reaction.